Hello everyone, my name is Mohammad Shafirpour. I'm a PhD candidate in the University of Manitoba, Winnipeg, Canada. This is the work of myself and my professor Vladimir Okhmatovsky. Today I'm going to talk about error control boundary element modeling of 3D plasmonic nanostructures by a higher order locally corrected Nystrom method. This is the outline of my presentation. A few words about the motivation, and then I will talk about the numerical methods studied. I will state the difficulty, the proposed method, higher order imperative in modeling plasmonic structures, and I will talk about characterizing plasmonic structures and modeling building blocks of electronic circuits. Motivation towards plasmonic nanostructures is that as the demand for smaller and faster electric circuits is there, researchers have been trying to use nanoparticles with very small dimensions to create different circuit elements. For example, here a waveguide has been created by putting nanoparticles, and also nano antennas have been proposed. So eventually we will have very small circuits which are very fast. So now that the research community is trying to create electric circuit at optical frequencies, numerical methods has to be developed for accurately analyzing these electric circuits. So in the numerical analysis, we should be able, we would be able to understand the physical coupling of individual particles, the propagation properties of the eigenmodes supported by the chain of such particles can be studied, and also impact of manufacturing irregularities can be rigorously analyzed. Now, how can we numerically analyze these nanostructures? Well, the good news is that nanostructures are small, but they are not too small that are affected by quantum effects. So we can actually use Maxwell equations to analyze them. Two types of formulations are available. One is differential equation and the other one is integral equation. Differential equations are good in the sense that they are simple to implement and they can be effective. But the problem with them is that you have to discretize the entire domain. But rather in the integral equations, you will just have to discretize the volume or surface of the object. So in this study, we use integral equations. This is a Schobert-Wilton-Glisson method of moment solution of volume integral equation. You can see that we use tetrahedrons to actually discretize the entire volume. Here, if we have a radial dipole excitation at 790 terahertz and the permittivity negative permittivity is actually the characteristic of metamaterials which form plasmonic nanostructures. So if we compare the volume integral equations with the mystery solutions, we can see that the error is at about 5% at the very best. So here we have 70,000 unknowns, and if we want to have more particles, let's say 100 particles, then we will end up having 7 million unknowns. And imagine if we have an entire circuit, we will have billions of unknowns. So volume integral equations would not be a good method to numerically analyze plasmonic nanostructures. So let's see why that happens. Here we can see that if we have a positive permittivity, which is a normal dielectric, the solution is quite accurate compared to the mysteries. But here, if we have negative permittivity, we can see that around the edges, the solution becomes inaccurate. And if we refine the mesh, the inaccuracies is still there. And here you can see that in the cross section, like this, we have very large error at the boundaries, and here also another cross section we still have those large errors. So we can see that the plasmonic nanostructures are quite sensitive to sharp edges. So we can go ahead and use surface integral equations, which is PMCHWT, and its name is due to its inventors. So here we only have basis functions on the surface, and we can see that the number of unknowns is actually reduced and the error is also decreased. So the magnetic current and the electric current are accurate, and their error is about 1 and 2%. So now we would think that this is a good solution. But let's look at the difficulty that we are facing here. Plasmonic waveguiding at terahertz frequencies has low attenuation in theory, but in practice they can have high attenuations. So for example, here in this case, the perturbed case, these nanoparticles are not placed in the equidistant spaces. So the distance between this particle and this particle might be different from the distance of this particle and that particle. So we can see here that even though in the ideal case the wave is being propagated, but in the perturbed case the wave has attenuated a lot. So when we have high attenuation, the numerically modeling these high attenuation cases is hard. The reason for that is that we have large dynamic range, and the effect of artificial sharp edges is so high. So here is looking at this difficulty from a familiar point of view. Here's the Mi-series solution for the perfect electric conducting material. We can see that the time snapshot is quite clear here. We have our dipole excitation here, and at 5 gigahertz we have this solution. But when we actually look at the solution, which is in the frequency domain, we see that the difference between the largest magnitude and the lowest magnitude has 4 orders of magnitude difference. So if we have 2 digits of precision at the high end, we have to have more accurate, we won't be able to capture the field here with 2 digits of precision. And for us to capture the field with 2 digits of precision here, we have to have more accurate numerical solution at this point. So let's look at it in the more numerical point of view. From the more numerical point of view, here if we actually use RWG method of moment solution using 9 triangle per wavelength, we can see that at the highest end the error is quite low, but when the magnitude of the actual solution is very small, the error grows, and at this point we have 30% error. And if we actually have more triangles per wavelength, we can see that the error decreases, but this is still unacceptable at 20%. So what we can do is that we use higher order method, and if we combine it with the non-uniform rational B-spline surfaces, we can completely eliminate the sharp edges. And here we can see that even with 380,000 unknowns at order 14, we can have a solution that at its best, it's 6 digits accurate, but even at those very small values, we have 4 digits of precision accuracy here. So we can actually formulate analytically the number of unknowns according to the desired accuracy, and we can actually find the optimal number of unknowns. Here is what we had before in our WG. We can see that at about 1 million unknowns, we can have 3 digits of precision, but here with the 14, with the solution at order 14, we can actually have 6 digits of precision even below 1 million. And we can see from this plot that if you wanted to have this accuracy using RWG method of moment solution, you would have to have 100 trillion unknowns. And let's say you wanted to have another solution which was only accurate up to 2 digits of precision at the lowest end, you still had to have 10 billion unknowns. So here we can see that we can actually have a minimum number of unknowns for desired accuracy. And if you have just a low order technique and you are wondering if you have to implement higher order methods, and you are kind of fine with having 1 million number of unknowns, you have to keep in mind that sooner or later you will have a problem that you have to have more accuracy on it, and at that point there is no way to actually climb up this curve. You might be able to climb up this, but you can never climb up this. So higher order methods are very efficient, especially when you need higher accuracy. So if you actually discretize the dielectric integral equation using EFIE, you can actually formulate LCN to solve for plasmonic nanostructures. You can see here that with the same example that we had before, we can have solutions up to 6 and 7 digits of precision. And here we can also have MFI formulated, and still higher order convergence can be achieved. And by combining them, you could of course get the combined field integral equation. Now here, if we actually use Mie series, you will have these dotted lines as we had it before, but these solid lines are created where the reference solution is the order 8 solution, and you can see that the error curve is almost identical to the one that we had the analytical solution. So if you actually use higher order solutions as the reference solution, we can actually verify the results that we are getting from the higher order method. So for example, here if we have 15 nanoparticles, these are the solutions using different orders, and you can see here that if we actually plot the error using order 8 solution, the larger error at the far end is still 3 digits accurate. The order 6 solution is 2 digits accurate. The order 4 and order 2 are not accurate, meaning that they have more than 10% error at the far end. So we could actually use either this or that depending on the engineering needs. And the importance of having these higher order techniques is that you can actually verify the numerical solution that you've got. So using this technique, we can actually try characterizing plasmonic waveguide just like we had in microwave engineering. For example, using short open calibration here, we can see that at the beginning of the entire system, which is error box 1 plus device under test plus error box 2, we have this point, and then at the far end we have this point, which is about the attenuation is about 10 times, and we know that using the order 8, this attenuation is easily captured, and you can see the open and short gates are pretty physical, and they are the numerical solution is basically giving us solutions that we expect. And here we are actually able to model the building blocks of metatronic circuits, which is nanoinductors, nanocapacitors, and this is the nano switch. Also, we can use the proposed method to formulate and analyze the multi-layered structures. It is possible to put a very small nano antenna on a large object, which is also quite challenging for numerical techniques, because if you have a very small object on a very larger one, it is difficult to capture the field due to this very small antenna on this very large object. And the higher order method will give you solutions that you can actually verify. And also, since this is a NURBS representation of the geometry, you can create arbitrary geometry, and you can accurately model the non-idealities that occur in fabricating spherical nanoparticles. So here I conclude my presentation. Integral equation method for plasmonic at terahertz frequencies. We studied the volume integral equation and the surface integral equations using low order methods. They are not efficient because for the volume integral equation they produce notably higher error. the PMCHWT, which is the surface integral equation, cannot achieve accurate solutions in modeling plasmonic structures because it has high attenuation, but the high order locally corrected Nystrom method can accurately model the plasmonic nanostructures. And the importance of the proposed method is that it provides verifiable numerical results by producing trustable reference solutions. Therefore, microwave techniques can be applied at optical frequencies, for example, short open calibration, and building blocks of metatronic circuits can be modeled accurately, and also non-idealities in fabrication of nanostructures can be modeled accurately. So with this, I finish my presentation. Please let me know if you have any questions.